Hello and welcome to another discussion on statistics. Today we are going to start our introduction on hypothesis testing, but we're going to start real slow and just learn about the normal distribution first, because it is a key element in the introduction and understanding of hypothesis testing initially. So if you recall a few lessons ago, we talked about the frequency tables and the histogram, and we maybe casually talked about the distribution of these values. Now, when you do a large enough sample of values and investigate that, or you have enough information, and you look at the histogram, you often see that it follows this bell-shaped curve, also called the normal distribution. And what people did at that stage, when they start to realize that many of these histograms exhibit a shape that looks like this, maybe a little bit narrower, maybe a little bit taller, but it has the same profile, they went and developed a theoretical function, a curve, to describe this that could then be analyzed outside of specific examples. When so many things follow this shape, not everything, but a shocking number of real-world variables follow this distribution. So let's have a look. That's one benefit to understanding this bell curve, is we can do more precise calculations. And like this, for example, before I say the other benefit, let's look at just a questionnaire being done, testing people's leadership skills and the scores that they got from many, sort of a smoothed out histogram, if you will. The scores ranged from 11 to 29 and so and anything in between. The more common values here around 20. 20 was the average as well. Now, before I go further in this example, let me jump to another example. This one is a questionnaire that tries to assess the person's ability to plan successfully and effectively. And they were scored 54 to 126, with 90 being the average. Both have the same kind of profile, this bell curve, this normal distribution. However, the scores were very different, right? The previous one had scores ranging from 11 to 29 with an average of 20. This one had different scores. How do we really compare them? If someone sits over here on the planning ability distribution, is that better or worse, more average or not, than if they sat over here in the leadership test? Now, depending on which two positions I look at, this one visually does seem further away from the center than this one, and it's on the other side as well. However, by standardizing this bell curve, we can better compare. Maybe the same person took these two different tests. We can better compare and better explain the observations that we get. And all we're going to do is count from the center, where the mean, the average, sits. We're going to count how many standard deviation steps the score is away from this mean. Instead of looking at the actual raw score that this specific distribution was measured with, we instead count the number of standard deviation steps away from the mean, which is going to be right here at 0. And we call that the z-score, or z-score, depending on where you're from. So in this case, in the planning ability example, my mean is 90. That's the center of this distribution. And my standard deviation is 12. So a score here sitting at wherever, I can convert to maybe a half a standard deviation step from the mean to the left. So negative means to the left, positive means to the right. So here, this one would be 84. So I can express the distance away from the center in terms of how many standard deviation steps or fractions of a step did I go and in which direction. So -1 would be a full standard deviation step below the mean. 3 would be 3 standard deviation steps above the mean. And if I do the same thing over here, let me just move up a touch. There we go. This one has a mean of 20 and a standard deviation of 3. So depending on the variability, how people responded, the standard deviation is not the same. The standard deviation in itself is a measure of the distribution. Now, in this case, a score here of 26 sits 2 standard deviation steps above the mean. So instead of referring to the raw scores, we can better compare these by standardizing them to their corresponding z-scores. And we can say the person here sits at a z-score of 2, whereas in the planning ability example, they sit at a z-score of -0.5. So they were much closer to the average in planning ability and much higher than the average in leadership ability. So the benefit to standardizing this is also that we can analyze this outside of specific examples and calculate the proportion of people or the population or whatever I'm investigating that sit these standard deviation steps away from the mean. And I can map this onto my leadership example distribution. I can map it onto my planning ability example, but I only need this one because it's standardized to just count standard deviation steps. It's just much more convenient that I can have one piece of information that can apply to many different examples, different means, different standard deviations. So people have gone to analyze this bell curve, this normal distribution, and roughly 34% sit in the first standard deviation gap above the mean and below. We have the symmetry. 14% fall into the range between 1 and 2 standard deviation steps, and 2% fall beyond 2 standard deviation steps. It's very rare to be that far away from the mean, but a small percentage do exhibit that behavior. So what do we get if we add these up, for example? We get 68, whoops, I'm writing on something weird. We get 68% fall within 1 standard deviation of the mean. If we add these further steps, we get approximately 96. Now, it's not exactly 96, but these are just convenient numbers, throwing away the decimals, to give me an idea of the sizes of these areas. And then, of course, if I look at everyone, then I'll get 100%, of course, right? Okay, so let's go back to our example, leadership example, and see how do we now calculate this a specific raw score from that specific test and standardize it to its corresponding z-score. So the formula is going to be, to calculate the z-score, I take the raw x value or score, take away the mean, and divide the whole thing by the standard deviation. That's one of the first things in a formula sheet that you can memorize. It's simple enough, or just look up. So in the case of a raw score of 26, we look at 26, take away the mean, so the distance from the mean, and then we have to put it in perspective using the standard deviation. We divide by the standard deviation and we get 2 standard deviation steps, which is exactly what we would think looking at it graphically. Okay, so this 2 counts specifically how many standard deviation steps and in which direction. So if we do a few more, let's look at a few other examples. Well, first, before I do that, let's backtrack and look at the other one before I flip the direction. Here we have the same formula. We want to, for example, look at a raw score of 84. What does that mean? Where does that sit? Instead of every time saying, well, the mean is 90 and the standard deviation is 12, so that means I'm sitting a little bit to the left. How far to the left? The z-score captures all of that right away. I calculate it, still the x, regardless if it's bigger or smaller, minus 90, everything divided by 12, I get negative 0.5, and that right away tells me it's half a step to the left of the center. Okay. So it has a lot of conveniences that over time we'll see more and more. The other issue could also be raised, that what if I have a z-score? What does that mean in terms of this specific example? For that, we're going to flip this formula around and just solve for x. We take the mean. I like to remember it, to be honest, the other way around, but hey, that's just me. It's of course the exact same thing, right? So I'm going to take the mean and I'm going to add a certain number of standard deviation steps. For example, if my z-score is 0, well, of course, I take 0 steps from the mean and I'm at the mean. If my z-score is 1, plug it into the formula if you don't want to think this formula, or think about taking a step away from the mean. What is my step? 1 standard deviation step. So I should get 23. Taking a 1 standard deviation step to the left, the calculation does exactly that and gets me to my raw score of 17. So I can go back and forth between these. They have the same information. For comparison purposes and for convenience, the z-score is there. Very convenient and a must. You can't live without it. It's too convenient. For this one, let's calculate maybe a z-score of 0.05. What does that mean in terms, how is that interpreted in terms of my specific planning ability example? Well, we already have it, but let's suppose we didn't. I'd go from 90. What distance do I step away? Well, negative a half times the standard deviation of 12, which would be 6. So the negative direction is left, positive direction is right. Z-score of 2 or Z-score of 1.2 rather. Let's do that one. Less obvious perhaps. I go from the mean, step away in the positive direction, 1.2 standard deviation steps, which means 14.4 in terms of the raw score, and I'm over here at 104, just beyond 1 standard deviation step. All right, so hopefully that gives you a taste of how we're going to look at things using the normal distribution, like that. Now the other benefit is that all of these all of this information has been already calculated for us in these tables. Now often they give you two different areas. You can choose which one, whatever is convenient depending on the situation. We'll do some examples shortly. Let's look, for example, at the very first one. A z-score of 0.11 means that it sits, remember, right, if I look at an example like this, z-score of 0.11 will be right there, right? Just beyond the mean. So this percentage over here is very small, very little sliver here, capturing 4.38% between the mean and where that score sits. Another way to interpret it is if I want to look from that z-score beyond to the right, then that captures 45.62%. And together they have to be 50% because of the symmetry, 50% on the right half, 50% on the left half. So we could, for example, look at what is a z-score of 1? Do I get this 34? Where does this come from? Well, it comes from these tables. A z-score of 1 would not be on this. I'm going to have to look at my more detailed table. 1, 1, 1. There we go. Let me just bring, it's a little big, but it's the same columns, same thing. I'm looking for this little sliver, maybe. Looking up, where is the z-score of 1? 34.13. See, so we just said 34. To remember it easily, it has a little decimal. All right. So we want to be comfortable in looking up the percentages, the proportions. There are also probabilities. If I want to ask, I can phrase it in many different ways. I could ask, what proportion of data points fell between the mean and one standard deviation step above the mean? If it follows this, it's roughly 34%. I can also ask it as a probability question. If I randomly select one of these data values, what is the probability that I'll fall between the mean and one standard deviation step above the mean? Well, 34% of the time that'll happen. Probability is 34%. And some decimals, but you get the idea. So whether I think of it as a proportion of the group or I think of it as a probability, these tables answer those questions. I can, of course, also reverse it and say, if I want to capture 23.89% of the population, how far above the mean do I need to extend my range? Z-score says 0.64, so 0.64 of a standard deviation step. If I have a specific example, I can then calculate, for example, 90 plus 0.64 times my standard deviation and get whatever I get. And then that would, over here, that would give me the range. That would capture just under 24% of the data values. Okay, so over time, we'll read this table more and more. Don't be concerned to understand it perfectly now. This is very much our introduction, and this whole topic will span a few videos because there's a lot to say. Let's look at, maybe you'd like some specific steps you could follow to help you figure out these percentages, or one way or another. Just adjusting my volume. I feel that I'm a little loud. Maybe not, maybe it's fine. Okay, so I am looking to perhaps calculate a percentage above or below a given score. What would I do? For example, before we look at the steps, let's suppose we are given a score of 125. How does that split up the proportion, the area under the graph? Well, I'm beginning with a raw score. I want to change it to the corresponding z-score first. I did that. Remember, x minus the mean standard deviation over there. That's my formula. So I got that. I got 1.67. There it is. Then it's not necessary, but especially in the beginning, it is very helpful to draw a picture of the bell curve. Have a rough idea of where this 125 sits, and therefore the 1.67 z-score. Color in some area for what I'm trying to find. Maybe I'm trying to find this tail, this area to the right. We're making up a question, right? Now, using my 34, 14, and 2 that I hopefully memorized, but it's not crucial, I can get an idea. Well, this sits a little below 2 standard deviation steps. 2 standard deviation steps and beyond would be 2%. I'm somewhere in the middle over here. I know it's not perfectly the middle, but maybe I get 4% to the right, and maybe I'm around 6%. That's my guess. It could be way off, but I just want to be in the area of the answer. So I'm guessing maybe 6%, right? I don't know. Just getting an idea. But I do want to be precise and calculate it. These steps 2 and 3 are optional. If I want to visualize it and think, well, what would I expect? I can do that, or I can skip it. I want to find the exact percentage using my table for the normal curve, the normal distribution. So I have a z-score of 1.67. Let's see where that is in the table. This one goes to 1.45. So I want to go to the next page, 1.67 over here. Now, depending on which one I want, I have 2 columns. If I maybe want this tail, we call it the tail only, this area, I would look in this percentage in the tail, 1.67, 4.75%, and that would be my answer. And then I can compare it, if I wanted to what I thought it would be. Does it make sense that it's 4.75? Well, it has to be more than 2. And it can't be more than 16, because then I'm within 1 standard deviation step. So all I know, it has to be beyond, or between rather, 16% and 2%. More than that, I don't really need to know, right? Somewhere in there, I got it a little closer to 2 because the drop-off it's not quite balanced here. So it is nice to think about what I get. So that's one direction. If I'm given a score, let's scroll up here. I'm given a score. I want to find the percentage above or below, depending on what is needed. I could also be given a percentage, and I want to find the score. Okay, so let's look at a diagram here, maybe like so, and say, let's suppose I want to calculate the score that would have 55% to the right of that line. Now I know that I'm messing up this a little bit, but I know that from the center beyond is 50%, right? I have perfect symmetry here. So really I'm looking for a 5% little sliver over here somewhere. It's my little sliver, that's 5%. So where do I think that score is going to be? Somewhere between -1 and 0. I don't know exactly which one it's going to be closer to. I like to say 0, but it's a little fatter at the top here, so I don't know for sure. but definitely between -1 and 0, right? Definitely. So I can draw a picture, use my 34, 14, and 2 breakdown, rough but still useful, and make a rough estimate. What do I think the z-score is going to be? I don't know. Let's say 0.4 negative. Why do I say that? Well, because it's not exactly halfway, right? I only have a little sliver. I'm just totally guessing. I'm not going to be right, but that's okay. It's a guess. And I definitely don't want to go close to -1. That would be 34% over here, and I'm just looking for 5. So I'm guessing -0.4. Don't know. Let's move on. Again, this 1 and 2 steps are optional, absolutely, but helpful in the beginning. Now I want to find the exact z-score using my table. How do I do that? Well, I have to look at the right column. And in this case, everything they give me is to the right of the mean, but because of the symmetry, I'm going to be okay. It's just so that they don't double up negative values and positive values when the area on either side is the same because of symmetry. So even though I am looking at a 5% on this side, I can also look at a 5% on that side, and these numbers will be the same in size. One's just going to be negative. So I can look for, I forgot what I looked for. Oh, 5%, right. I'm looking for a 5% little column here. I'm way too high, right? Let's scroll all the way up. Okay, here it's getting small. Here we go. Now there isn't one perfectly at 5. Different people do different things there. Most of the time they just take the average between these two, so 0.125, but it really depends. Sometimes they round to one or the other, but it seems like we're in the area of 0.12, between 0.12 and 1.3. Of course, we are negative. Which slide am I on? Here we go. So just to keep it consistent with this slide, let's take 0.13, but I would average them out if it's in the middle. Doesn't matter right now. So I get that from the table, right? I'll just say 0.13 so that it matches what you see here. So I get that from the table. I make it negative, even though the table values are positive. It's just on the other side. It's not a big deal. Because I have this symmetry, I can always exploit the symmetry. Then, so find the exact z-score using the table from your percentage. Okay. And we chose to look at the 5% sliver because the table needed that and it didn't give us a section bigger than 50%. Then, what did I think it was going to be? I thought -0.4. Well, I knew between -1 and 0. So I guess it's good. I was hoping maybe something less. Yeah, I wasn't sure. That's okay. And then, so checking it is optional, though a very good idea. Then if I want to find the corresponding raw score, I plug it into my formula. This is my mean. This is my z-score. That is my standard deviation. And I get 98.05. So scores above 98.05 cover 55% of the data values, the set or whatever I'm working with. So all of this just gives us time to look at the curve, work with these sections, use the tables. We just need exposure to this. Because a lot of what we're going to do in the future is this. Looking at a cutoff line, calculating some area, looking it up in the table over and over and over. So this first part of this section just gives us some exposure to this. All right, so now when we try and investigate larger situations Like, here's a little example. I want to know something about all the, maybe beans, I don't know, all the beans in the pot. But I'm not going to investigate every single bean, right? I'm going to take my spoon and take a sample. And whatever I see from that sample, or taste, or smell, or touch, I will conclude that the whole pot is probably similar. It's not necessarily accurate, but hey, it's the best I got. Or I have some area that I visualize, and I'm just taking a little circle of that because the whole area might have too many things. The whole circle might be too big for me. Or this is just another visualization of just taking some random selection of this area, whatever it might be. When I'm trying to investigate and make conclusions and say things about a very large population, like all Canadian women, I can't go and investigate every single person and interview them, right? It is practically impossible. So what we can do, though, is randomly select 50 Canadian women. And if we do that carefully, and there are techniques to do that, the 50 women we do then survey and sit down and investigate will hopefully be a fair and accurate representation of the whole population. However, because we are not examining the whole population, there will be some inaccuracy. But if our sample is large enough within reason, the distribution of the 50 Canadian women, whatever property we're investigating in our survey, it'll hopefully have a very similar profile to the population we are trying to actually investigate. It's just not practical. Let's look at maybe voting. All the voters. There's millions of them. There are too many. So what happens? We call up some random selection of voters and ask them how they're going to vote. And by using that information, we can get a pretty accurate, but not perfect, indication of how people in general might vote across the population. It's really, from a practical standpoint, all we have. We cannot go and call up every single citizen. Yet we still want to have more information than nothing, than just hoping for the best and watching how it turns out. We take a manageable sample, which could still be fairly large. And if it's large enough, and if it's spread across all the different groups and diverse enough, we get a pretty good estimation of the true distribution of whatever we are measuring. So I want to end this video just with an awareness. The difference between a population and a sample, okay, should be fairly obvious based on the pictures we just looked at. And to help distinguish these things in our minds, we're going to use different symbols to represent them. When we talk about the mean, think about the previous picture. Whatever I'm investigating, there is an average, there is a mean score among all women in Canada. We'll call that mu. The Greek letter mu will represent the population mean. When I take a sample, which will be less than all the people, the mean from the sample will be an M, the sample mean. Population mean, sample mean. Similar for the standard deviation. If I look at the standard deviation of the whole population, we'll use a sigma, the Greek letter sigma. And when I talk about the sample only, it's standard deviation. Now, different people use different things. We'll just use an SD for standard deviation. And of course, the variance is very closely related to the standard deviation. And we'll do that in the obvious way. Sigma squared for the population st squared for the sample. And to further separate these things in my mind, we'll call these parameters of the population. And when I talk about a sample, I'll call them statistics. Sample statistics, population parameter. So the goal moving forward is to figure out, thinking of these pictures, how do I use the sample statistics to tell me something about the population? That is the goal moving forward. But it is a multi-step process. There's a lot of things that we slowly want to build. So I'm going to pause the video here so that we don't talk for too long in one go. Until next time.